Hi everyone. So I know I said the last video was supposed to be the last video. It really was. My computer completely froze about 8 minutes into the video. I didn't realize this until I had made the entire video. Fortunately for me, there was only another 12 or so minutes, maybe 13, 14 minutes at the most after it froze. But as a result, I'm posting Video21 in two parts, part A and part B. And I already have the notes all written out. So I thought what I would do is just kind of go through the iPad, scrolling down and revealing key parts of the problem as I talk about it. I mean, the last video, it froze completely in that it didn't even, the iPad didn't even move. It was funny because from my perspective, I could see it moving. But then when I went to shut the meeting off, I realized the computer had frozen about 12 to 14 minutes earlier. But I could still see it in the meeting, which is really weird to see myself writing on the screen share. Anyways, so in part A of the video, I finished up this first example. So I'm just going to continue with the second one. So in the second one, we're gonna look at a slightly more complicated function, the ln of x cubed plus 6x. And we do recognize this as a function of the form ln of a function g at x, where now our g at x is the inner function x cubed plus 6x. And so we can use the formula I developed earlier in the lecture, in video 21, part A in the beginning, for the derivative of such a composition that we developed using the chain rule, which is g prime, the derivative of ln g at x is g prime at x over g at x. In this case, it's fairly straightforward because the g at x is so easy, relatively easy. So y prime then, derivative of this guy, is 1 over x cubed plus 6x times the derivative of the g at x, g prime, right? So the derivative of x cubed plus 6x, and that's just 3x squared plus 6. So when the dust settles, you get y prime is 3x squared plus 6 divided by x cubed plus 6x. So this is kind of like more like a traditional PowerPoint presentation where I'm kind of going from slide to slide. Okay, so what we can also do, and you'll see on the homework, is that we can combine these new rules we've learned about the derivatives of logarithms with the product rule, and kind of make slightly more complicated functions to differentiate. So that's what the next example does. So in the next example, we were asked to differentiate the function x squared plus 5x times ln of 3x. So this is a product of these two functions. Okay, so we use the product rule. The product rule says that the derivative of the product is the derivative of the first factor, so the derivative of x squared plus 5x, times the second factor, plus the first factor, times the derivative of the second. Right, so that's just the product rule, our good old friend, the product rule. Maybe it's been a while, but there it is again. Okay, so what do we get then? So the derivative of x squared plus 5x, that's easy. That's just 2x plus 5. So you get 2x plus 5 times the natural logarithm of 3x plus x squared plus 5x times the derivative of 3x, of ln of 3x. Now, this guy is of the form ln of some function gx, namely 3x. So I'll do its derivative here in gray. It's a relatively easy one. So the derivative of ln 3x, so this is our gx now, it's the function 3x, is 1 over gx, so 1 over 3x, times the derivative of 3x. But the derivative of 3x is easy. The derivative of 3x is just 3. So you get 1 over 3x times 3, and the 3's cancel, and you just get 1 over x. So what goes here is just the derivative here is just 1 over x. So we put that in, and so we get for y prime, we get 2x plus 5 times ln 3x, that was the first term, plus x squared plus 5x times the derivative of ln 3x, which we compute here, it's 1 over x. Then you could do some cancellation here. So this 1 over x can cancel with this x here, and it can cancel with this x squared to give you an x. And so when the dust settles, you get that y prime is 2x plus 5 times ln of 3x plus x plus 5. So that's the kind of thing you can do with these type of logarithm questions. You can also combine it with the quotient rule, but you won't have to do that, fortunately, in the homeworks. Those types of computations tend to be quite a bit more complicated. So we won't do those. The algebra for them doesn't work out nearly as nicely. So the other thing you can do with this that comes up with this, and it's important to be aware of, is that sometimes you can save a ton of work if you first use the properties of ln's, of logarithms, to simplify the function before differentiating. So, you know, in the last video, the last full video, video 20, in the beginning, I talk a lot about properties of ln's and the sum, the product property, the quotient property, etc. And we use those to solve their logarithmic equations. What we're going to do here is a bit the reverse. Instead of combining things into a single logarithm like we did it for those equations, we're going to use the properties the other way, separate things out to make the differentiation easier. Now, if you don't do this, it's not the end of the world, but you will cause yourself a lot more grief than is necessary. For example, suppose you want to differentiate the logarithm, natural logarithm of the root of 3x plus 7. So you could just go ahead and say, okay, gx is the root of 3x plus 7, and you could use, the formula that we talked about, like the derivative of ln of gx is g prime over g. But this g prime here is quite complicated, right? That requires another chain rule, because it's the composition of 3x plus 7 as the inner function with the square root as the outer function. So that requires another chain rule, and the answer you get if you didn't mess up will be quite challenging to simplify. We can save ourselves a lot of work by recalling the kind of exponent property for the logarithm, that the logarithm of a to the r is r ln a, that the exponent comes down. And then you recognize that we can write the square root, fix that up a bit. We can write the square root as a half power. So the square root of 3x plus 7 is 3x plus 7 to the 1/2. Then using this property, I can bring the 1/2 down, and then I get a much easier thing inside the logarithm, which I call h at x. So then I get 1/2 ln 3x plus 7. And so if I call that h, then I can now just take the derivative of this guy, and there's no square root involved at all. So I can bring the 1/2 outside the derivative ln 3x plus 7, call that h, and it's of course 1 over h. So it's 1 over 3x plus 7, 1 over the inner function, then times the derivative of 3x plus 7, the derivative of this h, right? So this is like this h prime here. And that's easy. I mean, derivative of 3x plus 7, that's just 3. So in the end, you just get that this whole thing here is just equal to 3, and you just get 3 in the numerator, so and then a 2 in the denominator, times 3x plus 7. Straightforward. So if you hadn't done this, and you'd gone ahead and differentiated, use the formula we were using in the last examples from the beginning, it would take you, even if you got the derivatives all correct, it would take you kind of a while to simplify your answer to this form. So another advantage of this is that using the property of logs first, is that you get an answer in a much simpler form. And if you want to work with it, it's much easier. Okay, so on a similar vein, I mean, even easier in some extent, is say if you want to differentiate the ln of 3 over x. So, I mean, the derivative of 3 over x isn't particularly hard, so maybe it's not as necessary to use the properties like it was for the last example. But again, it gives you the answer in a simpler form, so when you can, use the properties before differentiating. So the property I'm going to use here is ln a over b is ln a minus ln b, that quotient property. So if I do that, I can simplify ln 3 over x is ln 3 minus ln x. And now I'll differentiate this. Right, differentiate ln 3 minus ln x. Well, that's the derivative of ln 3 minus the derivative of ln x. ln 3 is just some number, right? Maybe a horrific, irrational number, but is number, right? It's whatever you have to raise e to get 3. The derivative of any constant, remember, is 0, so this just becomes a 0, and then you get the derivative of ln x minus the derivative of ln x, so you just get minus 1 over x. So in the end, you get minus 1 over x. That's it. Okay, so that concludes the video. This concludes our discussion for this week. And so this is the last of the material before the second test, right? So there's going to be, so now this is the material for section 4.5. And that's it. That's the last stuff before the test. So next week, there are no new videos, right? It's just preparing for the test, making sure you get caught up on all the work. All right, so hopefully, I don't think the computer froze this time, so I think we got through. Sorry about this, but at least it wasn't too long.